Assalamu alaikum. Hello everybody. Hope you will be fine. Today we will be discussing the stereochemistry of elimination reactions, reduced selectivity and stereoselectivity of the E2 reactions. Many reactions that lead to product mixtures of constitutional isomers from the same substance. There are a lot of reactions which might have the same substrate, but at the end the product will be a mixture of different isomers. Now, what is the reduced selectivity? The reactions that favor one or more isomer where the others are called reduced selective. E2 reactions are both reduced selective and stereoselective. The E2 elimination reactions are regioselective as well as stereoselective. What is the regioselectivity of E2 reaction? The more substituted an alkene, the more it is stable. When the alkene elimination reaction occurs and we get an alkene as a result, so if there are more substitution on the double bond, the carbons having the double bond, the more will be the stability of the product. The reaction leading to a lower energy product has a lower activation energy. Lesser is the activation energy, more is the stability. More is the stability, more is the product. Like if you see here in this diagram, you see here 1 hexene and 2 hexene. The 2 hexene that is highly substituted is of less energy as compared to the 1 hexene, and as we have that lower energy product has lower activation energy, lesser is the activation energy, more is the stability, so it is more stable as compared to the 1 hexene. The stereochemistry of elimination reactions. Now comes to the stereochemistry. If the elimination reactions removes two substituents from the same side of the molecule, it is syn elimination. Here, if you see to this molecule, both the heteroatom X and the hydrogen on which the base has attacked, the beta hydrogen which is to be removed, are on the same side. So this is syn elimination. Here if you see the X, that is the heteroatom which is to be removed, and the beta hydrogen which is to be removed by the base are on the opposite sides, so it is called anti-elimination. The X and the H are anti to each other, so these are called the anti-elimination reactions. The E2 reaction is stereoselective, which means that more of one stereoisomer is formed than the other. The stereoselectivity means that one isomer is selected or one isomer is more as compared to the other isomer. Take it for example this compound 2-pentene is obtained as the major product from the elimination reaction of 2-bromopentane. It's 2-bromopentane. In the presence of base, elimination reactions occurs, and there's the possibility of two products. The two products are that one is E2-pentene. The other is Z2-pentene. E2-pentene is formed more than the Z2-pentene. Okay. E means, these are two German words. E mean entgegen, opposite. The bulky groups are opposite to each other. Z means zusammen. The bulky groups are together on the same plane. They have the same plane. This is Z2-pentene. The Z2-pentene is only 14%, while the E2-pentene is 41%. So, that compound is more stable, in which the bulky groups are on the opposite sides. We can make a general statement about the stereoselectivity of E2 reactions. If the reactant has two hydrogens bonded to the carbon from which a hydrogen is to be removed, both the E and Z products will be formed, because there are two conformers in which the groups to be eliminated are anti. The alkene with the bulkiest group on opposite sides of the double bond will be formed in greater yield because it is more stable alkene. It means that if there are two hydrogens on the beta carbon, so both E and Z products are possible, but that product will be in greater yield in which the bulky groups are on the opposite sides. Looking to the example here, these are the two bromopentane. This is syn-periplanar and this is antiperiplanar. But the bromine and hydrogen are anti to each other in both cases. Now in this case we will get E2-pentene, which is more stable, entgegen. Both the bulky groups are on the opposite side. While in this case we will get Z2-pentene, which is less stable. And as in the previous slides, we have seen that the product of this is 41% and this Z is only 14%. Elimination of HBr from 3-bromo-2,2,3-trimethylpentanes leads predominantly to the E isomer because this stereoisomer has the methyl group, the bulkiest group on 1sp2. This is 3-bromo-2,2,3-trimethylpentane. 3-bromo-2,2,3-trimethylpentane. When elimination reaction occurs, so there is possibility of formation of two products. One is 3,4,4-trimethyl 3,4,4-trimethyl 2-pentene, and the other is Z 3,4,4-trimethyl 2-pentene. This is Z and this is E. If you see the bulkiest group of on 1sp2 carbon, that is tertiary butyl, and the bulkiest group of the other sp2 carbon, that is methyl, they are opposite to each other. This is more stable as compared to the two bulkiest groups on the same side. If the beta carbon from which a hydrogen is to be removed is bonded to only one hydrogen, there is only one conformer in which the groups to be eliminated are anti. Okay, if the beta carbon has only one hydrogen, so one conformer is possible where the hydrogen will be empty to the leaving group. Therefore, only one alkene product can be formed. So there is the possibility of only the formation of one product. The particular isomer that is formed depends on the configuration of the reactant. For example, anti-elimination of HBr from 2s3s3-bromo-3-phenyl butane form the E isomer, whereas anti-elimination of HBr from 2s3r2-bromo-3-phenyl butane form the Z isomer. The groups that are not eliminated retain their relative positions. I will go to explain it, that if there is the possibility, there is only one hydrogen, so there is the possibility of one isomer, the formation of one isomer. In this case, we have no choice that to have the bulkiest group on the opposite sides, and we will get the isomers, E isomer in one case and the Z isomer in other case. This is the, like here, 2s3s 2-bromo-3-phenyl butane. So in this case, we have no choice to get the Z isomer, because here on carbon there is only one hydrogen which can be removed, and we will get exclusively E2-phenyl 2-butene. But in this case, again, the 2s3r2-bromo-3-phenyl butane, we have one choice of removal of this hydrogen, and we will get exclusively the Z product. The E2 reaction is stereoselective but not stereospecific. If the two beta hydrogens are available on carbon bearing elimination of hydrogen, if there are two hydrogens available, again we will go to the example of 2-pentene. So 2-bromopentane, if you see here, two hydrogens are available. So that hydrogen will be removed, which will give you the more stable product, or in which the two bulky groups are on the opposite sides, and that is the E2-pentene. The hydrogen leading to more stable E isomer is selected to be extracted from beta carbon regardless of stereochemistry at the alpha carbon. Okay. What will be the stereochemistry at alpha carbon? It is not counted. Only that hydrogen will be extracted exclusively, which can give you the E isomer, and that is in this case like 2-pentene. In an E2 reaction, the bonds to be eliminated to the substituent must be in the same plane. They must be periplanar, or in the same plane. In this course, E2 elimination will all go via antiperiplanar conformation. If we have the Newman projection, so these are the syn-periplanar and these are the anti-periplanar drawing, or rotamer or isomer of these compounds. Of any compound, this is a plane, this is syn-periplanar, because both the leaving group, hydrogen, and the X are in the same plane, while here they are in the antiperiplanar. When only one hydrogen is on the beta carbon, predominantly anti-elimination leads to high stereospecificity. Again, we are discussing, so if one hydrogen is available like here, so we will specifically get the E product. And if in this case, in the 2s and 3r case, we will specifically get the Z product. Now we will come to the E2 elimination from cyclic compounds. Elimination from cyclic compounds follow the same stereochemical rule as elimination from the open chain compounds. To achieve the antiperiplanar geometry that is preferred for an E2 reaction, the two groups that are being eliminated from a cyclic compound must be trans to one another. Like in the open chain compound, in the cyclic compounds also, the two eliminating groups should be trans to each other. In the case of six-membered rings, the groups being eliminated will be antiperiplanar only if both are in axial position. Okay. The groups to be antiperiplanar in cyclic compounds, this is only possible if these two groups are axial, are on the adjacent carbons and are axial, like here. H and X both are in axial position. These two groups must be trans to each other. Now, if you see that when there is mono-substituted hexane, so the equatorial position is more stable as compared to the axial position for the mono-substitution, because there is more room for a substituent in that position. So, as we have studied on the previous slide, that the two groups should be antiperiplanar, and for antiperiplanar, if the two groups are antiperiplanar, they must be axial. But the more stable position for the mono substitution is not axial but equatorial, so the elimination from the most stable position is, or most stable conformer, is not possible. And the less stable, in which the substitution is on the axial, so the elimination is possible only from the less stable conformer, which has the axial geometry, and from the axial substituent we get this product, cyclohexene. Stereochemistry of the E1 reaction. An E1 elimination reaction takes place in two steps. The leaving group in the first step and a proton is lost from an adjacent carbon in the second step, following the sets up rule in order to form the more stable alkene. The carbocation formed in the first step is planar, so the electrons from a departing proton can move toward the positively charged carbon from either side. Therefore, both syn and anti-elimination can occur. In the E1 reaction, as against the E2, there is first the formation of the carbocation. The carbocation is a planar compound, planar molecule, and the electron from the departing proton can move toward the positively charged carbon from either side. It means that in that case, the proton can be removed from either side with equal ease. As both syn and anti-elimination can occur in the E1 reaction, both the E and Z products are formed regardless of whether the beta carbon from which the proton is removed is bonded to one or two hydrogens. The major product is the one with bulkiest group on the opposite sides of the double bond because it is more stable. So there is no difference if there is one hydrogen attached to the beta carbon or two hydrogens attached to the beta carbon. The product will be formed, the E and Z, in equal amount, but depends upon that the bulkiest groups should be on the opposite sides of the double bond. Here, This beta carbon has two hydrogens. So the bulkiest groups attached are on the opposite side. So E is E2-butene, this is the major product, and Z is the minor product. And in this case, the beta carbon has one hydrogen available. This is the carbocation formed. And again, we get the E product as major product. 3,4-dimethyl-3-hexene. E is major product and Z is the minor product. So in E elimination, the major condition, the basic condition is that the bulky group should be on the opposite side in the even elimination reaction. Even elimination reaction from cyclic compounds, when a substituted cyclohexane undergo an even reaction, the two groups that are eliminated do not have to both be in axial position because the elimination reaction is not concerted. First, a carbocation is formed, and then the proton is lost from the adjacent carbon, and it doesn't mean that it should be axial or it should be equatorial. So as against the E2 reaction in which both the leaving groups should be on axial position, this is not the case in E1 reaction, and that's why that the more stable equatorial position can also undergo the E1 elimination reaction. Like here the case that the chlorine, the substituent, is equatorial, but it can also undergo E1 elimination. Like first the chlorine has been removed and we get a carbocation, and then a proton has been removed from the axial position and we get a cyclohexene molecule. This lecture was prepared from these two books, Organic Chemistry by Claydon and by Paula Bruce. Thank you very much. Thanks.